Hello again. So, what we're going to talk about today is how to calculate up the RPMs for various cutting situations on a CNC mill. Now, the most common one, of course, is milling, and we can use a variety of different cutting tools for that. Things like end mills, face mills, shell mills. The list can go on for practically ever. The other second probably, and maybe even in some cases even more common than that type of cutting tool would be a drill and drilling operations. So drilling, tapping, countersinking, counter boring, etc. So that's what we're going to do today is show you how to come up with that. So I'm going to talk to you about the formula right here. I've got it right here already. Okay, so RPM, in case you don't know, that stands for revolutions per minute, and it does not have to be converted to metric or English or vice versa. It's always going to be RPM, so that's great. So here is the formula. You need to write this down, copy it. I highly recommend you, if you're going to be in any type of machining situation for any period of time, this needs to be etched in your brain. Seriously, okay? Because you not knowing this is going to make you look like a super amateur. All right, so first off, CS. What is CS? CS is cutting speed. Now, cutting speed is a pretty generalized type of a term. It basically means that it's basically how fast we can cut the material that we're cutting, and it's determined on lots of different factors. And I like here cutting speed is determined by factors like what's the cutting tool material made of? Is high speed steel? Is it carbide? Is it cast alloy? Is it cubic boron nitrate? Is it diamond? And again, there's just a whole lot of them out there. Each one of those is going to have their own individual cutting speed. The second most important variable in that equation would be the workpiece material. How hard is it? How soft is it? How tough is it? Aluminum is very soft. We can cut it much faster. Most tool steels are pretty hard, so we can't cut them as fast. Stainless steel is very tough, and hardness and toughness are not the same thing. Uh, Glass is hard. It takes diamonds to cut glass, but is it tough? No. Hit it with a hammer, you'll see. Okay, so that's another thing that plays in the selection of your cutting speed. Setup rigidity. How rigid is your setup? I mean, if you got something that you think is going to get pulled out of there, you're going to want to go a little slower. And how old and how good is your machine? How big is your machine? How much horsepower does your machine have? And last and all, and certainly not most least important, is the amount of experience you have. Once you get to where you've machined a lot, you can just tell by the sound and the color of the chips, or even sometimes the smell, if you can smell, if it's not totally 100% enclosed inside a covered with coolant type of a situation. But experience plays a big role in what cutting speed that you're going to determine. Now we go on down to that, and cutting speed is expressed in what we call surface feet per minute. Now you can find recommended cutting speeds for all of these different situations all over the internet. I mean, everywhere. There's literally, I would say, in the millions, and I'm not joking. They'll both be expressed in, sometimes also expressed metrically. Uh, it doesn't matter about that. Bottom line is you can find it everywhere, but your most reliable source is the machinist handbook. Cutting speeds will be given to you in ranges. Like they'll say, you're saying, I'm using high speed steel and I'm cutting like 1020 cold rolled steel. You look that up in a chart. I will be posting some charts so you can look at them. Most of the time, I will give you the recommended cutting speed to use. No, not all the time. But when you look at these charts, you're going to see that the cutting speed is expressed in a range. It'll like say for like again high speed steel 1020 cold rolled, it'll say something like anywhere from maybe 70 surface feet per minute to 180. And you're going to go, what do I use? Well, what they're doing is they have no idea what your setup rigidity is. They have no idea what your machine condition is, like that. So they have to give it to you in a range. They're never going to say cut it exactly like this. Beware of charts that say this is the exact cutting speed you should use, because chances are it ain't right. Even if you don't come, RPM calculations are theoretical. What does that mean? It simply means we're getting close to where we think we should be. Better than guessing. You're still going to have to adjust it. That's why on a CNC control we have an RPM override dial. That's right. We can speed the RPMs up from the programmed RPM, or we can slow them down. Usually in 10% increments on some of the higher quality controls, as much as 2% increments. I've never understood why it had to be that that particularly controlled, but anyway, there it is. So we're going to head and not talk too much more about it. Cutting speed, that's it. We're done with cutting speed. Now let's talk about this. The rest, this 3.82, that's a constant. And if you don't know what a constant means, you need to take a math class. Seriously, if you're going, I don't know what constant means, I'm sorry. I feel sorry for you. Constant means it's never going to change. Constant means constant. So it's always going to be 3.82. It's always going to be 3.82. It is always going to be 3.82. Some places will round it up to 4. Don't do that because I'll be looking for you to be using this formula. So that's a constant. It's always going to be the same. Where'd it come from? I think it's a derivation of pi, but I'm not sure. Not sure. I don't know. I don't care. D. Now, if you look down here, this is where cutting CS equals cutting speed. D is the diameter of the cutter or the drill. And hopefully, again, if you're not sure with what the term diameter means, take a circle and go to the middle of the circle and draw a line all the way across from one side of the circle to the other. And whatever the length of that line is, that is the diameter of the circle. The radius of that is half of that. So radius is half the diameter. So let's say I had a penny that measured exactly 1 inch across the widest part of it. I would have a 1 inch diameter penny. I don't think there's such a thing, but I just use penny. Okay, the radius of that would be 500 thousandths or a half of an inch. Rarely, we don't use radius in these calculations, and it's best to stay away from radiuses if you can. Now, I'm going to tell you right now, some machines will, in the controls, when you actually input the diameter of a cutter for other factors, they're either going to be set up, some places will be set up for radius, and some people will be set up for diameter. That's a setting you can change yourself on just about any machine. So I don't know where you're going to land. You don't know where you're going to land. All right, so D, again, diameter of the cutter or the drill. Now there's a lot of things like center drills and counterbores and countersinks. This RPM calculation really doesn't fall into that. They don't fall into that category really well. Though some people will try to use them and you won't come up with great results. Again, when you're talking about RPMs for like again, countersinks, counterbores, tap RPMs are very important. That's a whole different type calculation. The general thing is if you're tapping, you're going to go ahead and do like if it's a half-inch diameter tap, you would do a RPM calculation for half-inch diameter end mill or drill, and then divide that by 3. 1/3 the normal speed. That's what the machinery's handbook will tell you. If you don't believe me, look it up. I know it. I teach this thing, and also I've been using it since I was 16. I'm 58. I know the machinist handbook. It changes every year, but every 3 years or so, but I know it. So there we go. That's our so RPM. We just take whatever cutting speed I give you, multiply it times 3.82, and then you're going to divide it by the diameter. Now, there's a couple things you have to do. You have to be able to convert the diameters into decimals because most of the time your fractions won't work. So let's just do a little decimal equivalency work right here. We'll pop up with the old calculator. Again, you don't have to use this calculator. I think I can actually, no, I cannot. I thought I could make this thing bigger. It does not let me make it bigger. View, let me see that. I've never tried to do that. Uh, it always gives you the history. Let me see, edit. No, let's forget it. We won't worry about it. We'll just bring it back up. You click any place, the calculator goes away. I hate that. There's got to be a way to keep that from happening. One of these days I'll figure it out. So, decimal equivalency. Let's say you had a 1/4 inch drill. So, 1, that is a division problem. 1 divided by 4. Okay, that's what a fraction is. Yeah, it's just a division problem. Equals, that's the decimal equivalency right there of a 1/4 inch, 250 thousandths. That's right. So see, you don't really need a decimal equivalency chart to take fractions to decimals. You've got a calculator. But going back, and if I say like, oh, let's clear that out, and I say, so what is this? There's 187 thousandths and 5/10. Now I know several people already know. They go, no, I know what that is. I know what it is because I got them memorized all the way down to a 16th. That's 3/16. You don't believe me? I know you don't. See, 3 divided by 16. Ta-da! 187 thousandths and 5/10. 187 thousandths and 5/10. That is how you say that. You want to sound like amateur? Go 1.875. or say 1875 thousandths. Or don't talk like that. That immediately will set you up in a shop as somebody that they're all going to target and do not, well, you know what they'll do. If you've never worked at a job before, you don't. Guess what? They're going to give you a hard time. That's what they're going to do. So let's try one more. We'll clear that out. What's the decimal equivalency in 9/16? It's 562 thousandths and 5/10. I know that, but you don't. I know some people in this class do. They're 562 thousandths and 5/10. So we're going to learn that later on. You're going, well, what's this got to do with RPMs? So that was always somebody whining. Well, to quit whining, okay? Here's what we're doing. We'll go ahead and do one. I have a little quiz right here, all set up for practice. By the way, you also have an RPM calculation quiz that's going to pop up in your Module 1. Look for it and check out the due date. Remember, I'm not going to tell you, it may not be in Module 1, but it will for what I'm posting tonight. So, all right, so let's do something here. Here's the cutter diameter, it's 3/4, and the cutting speed's 120. So let's just do one real quick. So what do we got to do? I got to take 120 times. Now, you can't put 3/4 in there. I mean, you can. I'd have to put parentheses in there. It's just easier to say, I know what that is. It's 750,000. So we're going to take 120 times 3.82. You can put this in memory. That'd be cool. Memory store. Boom. All right. Okay, equals this. It'll equal some weird number. That is not your RPM. I'm going to go back over this again because I know I'm talking a lot, but that is not your RPM. That is just that. We're going to take that and divide that number by our diameter, which, like I said, is 3/4 of an inch, which if you don't know your decimal equivalencies, you need to. And I'm probably going to be putting up decimal equivalency quizzes, but you'll all just use your charts and stuff like that. Again, you can find decimal equivalency charts everywhere. It's 750 thousandths. So let's take a look at that. 611. Well, I'm looking over here. None of the responses provided. Well, let's clear that back out and try it again. Make sure I wasn't wrong. Again, the cutting speed's 120. That's about a standard for aluminum using high-speed steel. That's my experience. Times, again, the constant, 3.82 equals this, divided by the decimal equivalency of 3/4, which is 750 thousandths. Yes, 611. The answer to this one would be none of the responses provided. I am not going to put that in there. Let's go down to, here's just another one here. Okay, so we'll do 3 or 4. We're not going to do a bunch. This time we're doing a drill. Like I said, it's the same thing. Using a cutting speed of 175, so I'm going to use the keyboard. 175 times 3.82. You could have gone memory recall. I'll do that next time. Equals that divided by and 7/16. Well, I happen to know the decimal equivalency of 7/16 is 0.4375. See, it is so much easier to memorize this stuff. Now, do I know it down to the 64ths? No, I do not. I have some students who know a lot of the 64ths. We're looking at 1528. Well, that's not an answer here. None of that responses. You're going, are you sure? Well, we'll do it again. So the cutting speed's 175, and times 3.82 equals this, divided by 0.4375. Yeah, you're going, well, why isn't the right answer here? Because I don't always give you the right answer. I give you none of the responses provided. Yeah, get used to that. That's pretty popular. I choose those a lot. So, but that is the right answer. Oh, let's clear that out. We can try the memory thing next time. Let's see if it'll save you some time. Okay, this time I actually give you the cutter diameter, 562 thousandths and 5/10. If you remember, that was 9/16. Just showed you that. We're going to use a cutting speed of 100. So 100 times 3.82 doesn't take a genius to come up. Well, let's try that again. Not sure. Oh, I didn't have it yet. So 100 times 3.82 equals, 382. Divided by 0.5625. See, you don't have to do a decimal equivalency problem on that one. You got it. Boom. It says 697.111111 forever and ever and ever. Okay, let's talk a little bit about rounding and the way that works. 679, is the correct response. It's right there. All right. You will never put in a decimal point in the speed. Now, spindle speeds are always going to be the S word. You're going to be MO3, which is usually spindle on forward, followed by an S word, and whatever. In this case, it would be 679. There's no reason to don't put a decimal point in there. 90% of the controls out there will error out if you put a decimal point in your spindle speed. Later on, I'll make sure I'll bring that back up to you. I said I was going to use the memory. I keep forgetting to do that. Let's just try the same thing. I already know what it was, right? 100 times memory recall, boom, equals that divided by 0.5625. Boom. Oh yeah, see, that works. So you can do that. Again, whatever calculator you want to use, you do not have to use this calculator right here. Now, for those of you who really want to learn a little more, let's go view scientific. Oh no, Randall, what are you doing to us? I got parentheses. Let me show you how I can do it this time. I go, now, let's say I didn't know. Let's go to a different, here, wait a second here. I'll come back to that. We'll go to a different one. This one right here. Okay, inch and a quarter. That's not a good one for this example. Let's try this. 1/8. Excellent. Okay, this will work. So, by viewing scientific, I get the parentheses, which means anytime we put something in parentheses in a calculator, it means do that first. Okay? All right, so watch how this works. I'm going to hit memory clear. No more 3.82. I'm not going to use it in this case. Just showing you another way to do this. So here our cutting speed is 45. So I'm going to say 45 times, again, our constant, 3.82. Always going to be a constant. Okay? And then I'm going to put one of these here. Okay? Am I? Maybe not. I love that. It's supposed to be a back button. Doesn't go back, does it? Oh, just clear that all out. You know what? I don't do this on this calculator. I do it on my other calculator. I have a TI-80. A TI-35 will give you the parentheses too. So rather than fighting that and making sure that that doesn't work, I'll go ahead and do this again. So we've got 45 times my cutting 3.82, which is again my constant, equals this, and divided by the decimal equivalency of 1/8 of an inch, which I know is a 0.125, 125 thousandths. You can say 0.125, but again, so 1375. See, yeah, right there's the right answer. All right, so let's just do a couple more here. Come on down here to some more that I haven't seen in a while. This just says questions 10. I would like to have different questions. We'll just make up, we'll use this one right here. It's pretty cool. So clear it back out. Again, I'll put the 3.82 back in my constant into my memory there. Memory store, boom. Okay, clear that back out. So if I have memory recall, there it goes, clear. See, that's how that works. I think different buttons on different calculators. If you don't know how to use your calculator, I can't help you. That's not part of my job in this class to teach you how to use your calculator. All right, so what do we got here? We got, again, so we're going to take our cutting speed, which is 50, multiply it times our constant. Okay, very good. So 3.82 equals this, and divided by 11 sixteenths. Now 11 sixteenths is 687 thousandths and 5 tenths divided by 0.6875. Now I showed you how to come up with that. So equals, boom. All right, is that it? I don't know. Well, I got 278. Notice I rounded it up. Yep. So, you know, that time I did put the 3.82. I'll do it again, this time using the memory recall button. So, again, cut 50 times 3.82. Right? No, let's go back. There's no way to go back. Let's see if it goes back. This one goes back, but the other one wouldn't go back. Interesting. The scientific calculator would not let me use that button. Stupidity. Whatever. It's my stupidity, I'm sure. So let's start again. 50 times memory recall. Clear that. 50 times memory recall equals divided by 0.125. There's my RPM, right? Oh, did something wrong. Let's try it again. 50 times memory recall equals this divided by 0.1125. This is the hard way to do it. The keyboard is much easier to use. 1528. Well, I'm looking at that going, huh, all right, that's still not right, is it? What am I doing wrong? If you're not watching the video, you're going, I don't know. Well, it's because I'm doing this. Here's what I'm not. I used 1/8 of an inch, didn't I? Yeah, not 11/16. You got to check that. I do that lots of times to make see if people are actually paying attention to me. Let's try it again. 50 times memory recall equals divided by 0.6875. Yeah, see, it wasn't 1/8 of an inch. It was 11/16. Boom. 277 rounded up to 278. All right. So to recap, one, when you do this, the first thing you need to do, I'm going to get rid of that, is on any of these problems, let's go back up to this one here where I'm not giving you a decimal equivalency. You need to convert this to a decimal. Remember, 3 divided by 4 equals, that's your decimal equivalency. Or better yet, just memorize it. Now, there's no way I can have you memorize them in an online course because you just won't. And so I'm not going to even try. All right? It's in your best interest to do so. And, if you know anybody that's a machinist, ask them. I can rattle them off right now, but it's just wasting your time. Like I said, I even know some of the 30 seconds. So I know them all the way down to the 16th, some of the 30 seconds, and a few of the 64ths, but not all of them. You can get a decimal equivalency chart any place. Just type in decimal equivalencies on the old on the old internet, and by God, you'll pump up one. I could post one, which I probably will. And some people are going to ask me, don't I get my CNC handbook? We'll see if we can do that. There's something I've got, but I don't know how I'm going to get it to you. So, all right. I don't think I'm going to do any more in this video because it's pretty simple, and probably by now most people already stopped watching. So, have a good day. 3, 2.